Today I will be teaching you about time complexity. What will you learn from this video? First of all, we will talk about complexity calculations. These are calculations involved in counting the number of operations our program needs to complete a certain task. Secondly, we will talk about common complexities and constraints. These are time complexities which are very popular in programming contests, such as binary search, sorting, reversing, and many more. In the third point, we will go through constant factors. These things are very crucial for contests that have a very strict lower bound. In the last point, we will talk about the formal definition of the big O notation. This is a mathematical formula for the complex big O notation that it is. Time limits in contests. In programming contests, there is a strict limit on program runtime. This means that in order to pass, your program needs to finish running with a certain time frame. For your Usaco, this limit is 2 seconds for C++ submissions and 4 seconds for Java and Python submissions. C++ is way faster than Java and Python. That's why it has only 2 seconds of runtime available. But because Java and Python are slower, they have 4 seconds available to them. How many operations can we make in a second? A good approximation is 10 to the power of 8, but with good constant factors, we can achieve 5 times that. So, if we know that our program with good constant factors can achieve 5 times 10 to the power of 8 in 1 second, in 2 seconds, we just need to multiply this by 2. So 2 times 5 times 10 to the power of 8 will be 10 times 10 to the power of 8, which will be 10 to the power of 9. And this is the number of operations that you can make in our submission time. Timing your program. We want a method of characterizing how many operations it takes to run each algorithm in terms of the input size n. Fortunately, this can be done relatively easily using big O notation. What's a big O notation, you may ask? Well, big O notation expresses worst case complexity as a function of n, as n gets arbitrarily large. Complexity is an upper bound for the number of steps an algorithm requires as a function of the input size. In big O notation, we denote the complexity of a function as O of f of n, where f of n is a function without constant factors or lower order terms. What does it mean, you may ask? Well, let's debunk this complex definition of the big O notation into 2 cases. Let's solve the first case right now. The big O notation expresses worst case complexity as a function of n. Alright, big O notation is a function of n. So, it's a function, we are given an n. So, if it's a function, then we can create a graph like this one here. And if we are given n as our input, we're going to have n here and O of n right here. Okay, so let's suppose that our O function is like this. Okay, let's read further as n gets arbitrarily large. So now we know that n can go into infinity. Complexity is an upper bound for the number of steps an algorithm requires as a function of the input size. So let's suppose that f of n, as small n, is the time taken for our algorithm to do its job, given an input of size n. So for example, n can be the size of an array that is given to us. For example, can be our array and has 1, 3, 4, 2, 7, and it has length n equal to 5, and our function f of n would be equal to f of 5, because n is equal to 5 in this case right here. So let's read further. Complexity is an upper bound for the number of steps an algorithm requires as a function of the input size. So right here we defined a function that is given an n, the size of our input, and gives the time taken for our algorithm to do its job. And that's this portion of our statement right here. Now we need to solve this statement. Complexity is an upper bound. Okay, so we need to calculate a function O of n that is always bigger or equal to the output of f of lower n. But you may ask yourself, well, what is this big N? What does it mean? Big N is equal to f of n, because we want to calculate the upper bound for this function. So this definition can be written down to a form like this: O of f of small n. Let's explain the second part of the big O notation. In big O notation, we denote the complexity of a function as O of f of n, where f of n is a function without constant factors or lower order terms. We know the first half, so in big O notation, we denote the complexity of a function as O of f of n. This we all know because I explained it to you in the previous section. Now we need to debunk this part of the question. Let's see. Where f of n is a function without constant factors or lower order terms. Okay, we know that O of f of n is our big O notation. Let's suppose that f of n is equal to this form: n to the power of 4 plus 27 times n to the power of 3 minus 9 times n squared plus n plus 153. And here we read that we need to do something with this function to be put into the big O notation. First of all, we need to erase constant factors. What are constant factors? Constant factors are just constants in a function. So for example, 153 is a constant. 3/3 is a constant. The square root of 5 is a constant. 12 is a constant. These all are constants. But n squared is not a constant, it's a variable. X is also a variable. Y times z is also a variable. And m is also a variable. So they are not constant factors. So now we know what are constant factors, and we need to remove them from this function definition. So now let's try to do this. Is n to the power of 4 a constant? No. N to the power of 4 is a variable. Is 27 a constant? Yes, it is. So let's erase it. Is n to the power of 3 a constant? No, it's not. It's a variable. Is 9 a constant? Yes, it is. So we erase it. Is n to the power of 2 a constant? No. It's a variable. Is n a constant? No. It's a variable. Is 153 a constant? Yes, it is. So we erase it. Now, after all of these operations, our function f of n will look like this. N to the power of 4 plus n to the power of 3 minus n to the power of 2 plus n. Now we understand constant factors. Let's erase all the lower order terms. What are lower order terms, you may ask? Well, in a function f of n, we have so-called terms. Right here, n to the power of 4 is a term, n to the power of 3 is a term, n to the power of 2 is a term, and n is a term. We can write them out right here. N to the power of 4, the first term, n to the power of 3, the second term, n to the power of 2, the third term, and n, the fourth term. Now, what are lower order terms and what are higher order terms? Well, we know that n approaches infinity. So, if we put as n a really big number, then n to the power of 4 will be always bigger than n to the power of 3 and n to the power of 2 and just n. So, a higher order term will be always bigger than any lower order term if we put a number big enough, any number big enough. So the highest order term in here is n to the power of 4. Why is that? Well, if we put, for example, 1000 in here as n, it will be a much bigger number than n to the power of 3, n to the power of 2, or n. Now we know what are higher order terms, but what are lower order terms? Lower order terms are just the reverse. So if we put a big enough value, we can make this always smaller than n to the power of 2, n to the power of 3, and n to the power of 4. So now we know what are lower order terms and higher order terms. We need to remove all lower order terms. We know that we only have one higher order term. right here, n to the power of 4. So we remove the rest. F of n, if we remove all the rest, will be just equal to n to the power of 4. And now we can see that our big O notation for this very complex function will just be n to the power of 4. So right here, big O notation, big the big O notation will be O of n squared for this complex f of n. Now let's go through some examples. Constant time operations. Constant time operations are operations if we put a n even, for example here 5, there will be only one operation, assignment. If we put, for example, n equal to 7, we'll still only have just one operation. So, a constant time operation is an operation even though n is equal to, let's suppose, this big number, we perform a constant number of operations. We mark this as O of 1. Why is that? Well, because from the previous definitions we know that first we remove constant factors, remove and secondly we remove lower order terms. If, for example, n is equal to 5, so f of n, f of 5, like f of n is equal to f of 5, and our function is constant, so our function will look like this. It will have a straight line. It will have the definition like f of n is equal to, let's say, 7 operations. Even if n is equal to 1 million, we would do just 7 operations. Now we want to have a O definition, big O notation of f of n. We know that we have f of n equal to 7. We must remove constant factors. So we will remove the 7 and remove all lower order terms. We do not have any lower order terms. And if we do all these operations, f of n will be equal to nothing. Well, it's not possible that f of n is equal to nothing. We must give some value to it, and by default we put a 1. So O of f of n is equal to O of 1. For and while loops. In the following examples, we assume that the code inside the loops is O of 1. The time complexity for loops is the number of iterations that the loop runs multiplied by the amount of operations per iteration. The following code examples are both O of n. So we know that this is constant time, so O of 1 is our constant definition, and this loop runs n times. So we just multiply n times 1, which is obviously equal to n. And here, we know that this code runs in constant time, so O of 1, and this loop runs for O of n time, so O of n times 1 is equal to O of n time, right here. Loops inside loops. We can find the time complexity of multiple loops by multiplying together the time complexities of each loop. The following example is O of nm, because the outer loop runs in O of n iterations and the inner loop in O of m. So we know that this here is constant time. This loop runs for an m number of iterations. This one runs in m. So we just multiply n times m times 1 equals to nm. Constant factor. Constant factor refers to the idea that different operations with the same complexity take slightly different amounts of time to run. For example, 3 addition operations take a bit longer than a single addition operation. Another example is that although binary search on an array and insertion into an unordered set are both log of n, binary search is noticeably faster. Constant factor is entirely ignored in big O notation. This is fine most of the time, but if the time limit is particularly tight, you may receive time limit exceeded, or otherwise called TLE, of the intended complexity. When this happens, it is important to keep constant factors in mind. For example, a piece of code that iterates through all ordered triplets when in n to the power 3 time might be sped up by a factor of 6 if we only need to iterate through all unordered triplets. For now, don't worry about optimizing constant factors, just be aware of them. Tips. If an algorithm contains multiple blocks, then its time complexity is the worst case time complexity out of any block. For example, if an algorithm has O of n block and an O of n squared block, so these here are two different blocks of code that are inside our main algorithm, then the overall time complexity is O of n squared. Why is that? Well, if firstly we compute O of n and then we compute n squared, we add these two, which will be equal to O of n squared plus n, and we know that n is the lower order term of n squared, and we will have O of n squared. Functions of different variables generally are considered lower order terms with respect to each other, so we must include both terms. For example, if an algorithm has an O of n squared block and an O of n times n block, the overall time complexity would be O of n squared plus nm. Where is that? This is the same operation as we did right here, but we now know that we need to erase lower order terms. But really, nm is not the lower order term of n squared, so we cannot erase it. So we just leave it there. The time complexity will be still n squared plus nm. P versus NP. P refers to the class of problems that can be solved with polynomial time. So for example, right here is the class of problems that can be solved in polynomial time. So n squared, n to the power 3, n to the power of 100, these are polynomial. NP, short for non-deterministic polynomial time, right here, is the set of problems which solutions that can be verified, not solved, just verified in polynomial time. And a common example of a problem in NP is a generalized version of Sudoku, where a solution is easily verifiable in polynomial time, but it is unknown whether a solution is computable in polynomial time. P versus NP is the classic unsolved problem that asks whether every problem that can be verified in polynomial time can also be solved in polynomial time. Common complexities. So, a mathematical formula that just calculates an answer has an O of 1 complexity. Binary search, log of n, unordered set or map operation of 1, prime factorization of an integer or checking primality, n squared, reading in n items of the input, O of n, and of course sorting n log n. Here I present to you a guide that allows you to calculate the time complexity of your algorithm needed to solve a particular problem. So for example, if in a programming contest the n, so the size of your input, is given to be lower or equal to 10, your algorithm or your solution can have a time complexity of n factorial, n to the power of 7, or n to the power of 6. This doesn't mean that it should have these complexities, but it can have those. But let's suppose if n is less than or equal to 10 to the power of 12, our complexities cannot be so big, because we will have time limit exceeded. Normally, you can compute only 10 to the power of 8 operations per second, which, if n is this large, if we calculate n factorial of 10 to the power of 12, like this, 10 to the power of 12 factorial will certainly be greater than 10 to the power of 8. That's why if n is less than or equal to 10, our time complexity can be this big, but it can also be smaller. So, if let's suppose n is less than or equal to 400, our time complexity can be here, n to the power of 3, and every other complexity from this range right here. So it can be n squared of n log n, and so on.